Today we have Sneh Pandya, who is a PhD student, fifth-year PhD student from Northeastern, and doing some really interesting work on domain adaptation using neural networks. So please take it away.
Thank you. Before I start, I guess I'll try to figure out where the best place to stand without totally obstructing my slides is. Maybe some version of here. But yes, thank you for the introduction. My name is Sneh. I have been in Boston for a long time, but this is my first time at the CFA, so thank you for the invite. And yeah, so I'm going to be talking about this domain adaptation algorithm that I've come up with my colleagues, Porter Patel, Brian Nord, Mike Walmsley, and Alexander Sprianovich. This is some work I did at Fermilab last year. I guess if you want to gauge how much you might find this interesting before I begin, if generalization of neural networks is something that you struggle with in your own work, this might be relevant for you. And in particular, we come up with this domain adaptation algorithm, a way of training models to help them generalize. But more so, this is like a all-encompassing prescription for what you might want to do to generalize, not just in something in the training, but also architectural decisions you can make as well. So it's quite canonical at this point to use cat images in ML talks. So here's a situation where you might want to classify cat versus dog images. So I have this cute cat. I have a fairly standard architecture. I have some convolutional layers that are learning, the features in my image, and then I have some linear layers at the end that are actually doing the classification. And this will work. This is something that people can do. ChatGPT can do this in a few seconds. That's all very simple, right? But if I take the same model and I perturb the distribution a little bit, so I take the same model, but I introduce a distributional shift that maybe now I don't have only cute cats and dogs, but now I have an angry cat. What can happen is that my model gets very confused, right? And so this is the problem of generalization. Neural networks, despite how predictively powerful they are actually kind of like a house of cards when it comes to perturbing the data distribution that they see. And so, yeah, their predictive performance drops with distributional shifts in data. And in science, of course, this is relevant for us as astrophysicists and cosmologists because frequently we're training models on simulations with the expectation that they will perform on real data. Or even more so, we're training models on legacy data with the expectation that we can deploy them readily on stage 4 survey data when we get it, right? And this is just simply not the case. From a more logistical standpoint, training models is expensive, especially now as we approach this sort of foundation model for X era. But also finite data is a commodity, right? So labeled data is a finite commodity, what I meant to say. So the labeled data we have at hand, we want to do the most we can to construct models that will perform on new data sets. And so there's a lot of shifts that are relevant when we talk about generalization. In this talk, what I'm going to be focusing on are what are called covariate shifts. This is the type of data shift where the data distribution is changing, but the conditional distribution of the labels is the same. Or in other words, the data distribution is changing, but the task is the same. So for example, I might be classifying galaxies from SDSS and wanting to classify the same galaxies in a new survey. And so in this talk, the question we're going to be trying to answer is how can we make neural networks more generalizable with the added asterisk of we want to do it in a way that's fairly semi-automatic and not too expensive, right? And so generalization is something that's extensively studied, of course. I think in the literature, you can group efforts of generalization into things in the training or things in the architecture. And so if you guys are ML people, you may recognize many of these things. On the training side, simple things such as early stopping, prevent overfitting, for example, data augmentation, ensembling models, of course. And on the architectural side, things like residual connections, dropout, and equivariance can also help generalization. In this talk, what I'm going to be focusing on, of course, is domain adaptation, but also on the architectural side, I'll be focusing on equivariance. And this is the idea of injecting models with symmetry priors that I know exist in the data distribution. So restricting the feature learning of models such that they're learning features that are quote unquote physical. And this has been well known to help the generalization of models as well. I guess before I continue, I'll just pause if there's some questions. Cool. So I'm sure you guys have heard of equivariance, or at the very least, you've probably heard people that can give better talks on equivariance than I can. So a very brief recap. Convolution is a well-defined mathematical operation, right? And convolutional neural networks have this benefit of being both local and translation invariant. So again, going back to this cat example, a CNN can understand locality in the sense that it'll be able to understand what parts of the cat image are the mouth, the eyes, etc. And I can shift that image of a cat, and the CNN will still be able to identify it as a cat. And this sounds very trivial, right? But this is not something you necessarily get out of an NLP. The convolution is very powerful in this sense. And so the idea behind equivariance is that I can lift convolution to, instead of being translation invariant, be invariant to any group G. And so this is the idea of leveraging any higher order symmetries that may exist in my data and inserting them into convolution. So for example, especially in science, or in astrophysics, we're frequently operating in the setting where rotational invariance exists in our data. So for example, galaxy images, there's no canonical reference frame in the universe, so I can rotate a galaxy, and its morphology will stay the same. And so this is the idea behind equivariant models, is injecting these higher order symmetries directly into the feature learning, such that I learn features that generalize, assuming that the same symmetries exist throughout the data I want my model to generalize to, which is usually an okay assumption to make. And so yes, the data frequently contains these higher order symmetries that can be exploited. And as a result, these equivariant neural networks are more data efficient, and they also learn more generalizable features. And then at least for this talk, the sort of equivariant models we're going to be interested in, or the extent of equivariance you'll encounter, is dihedral group equivariant models. This is the discrete subgroup of O2, basically symmetries of the n-gon, so discrete rotations and reflections. Cool. So now for domain adaptation. So domain adaptation is an older idea in ML, sort of predating even like 2012 AlexNet revolution. And the setting here is I'll have some source domain data I call X, and my target domain data I call X star. And only my source domain data is labeled, right? I'll have a neural network f of theta, and my neural network can make predictions on both data domains. And my neural network must also admit what's called a latent vector, latent representation, latent space. I'll sort of use these terms interchangeably. But you can consider that to be the representation extracted from the last fully connected layer of the model. Sort of more qualitatively, you can consider this latent vector as a distilled lower dimensional representation of what the model has learned. And so this is the setting we're going to be operating in. And it'll be sort of clear in a bit why we need to isolate these latents. But the idea behind domain adaptation is that if I can align the latent representation of my model between the source and target domain, I can then improve feature learning in that I'm learning features that persist across data domains, despite my target domain data not having latents, right? So this is an unsupervised thing I'm talking about. And then in practice, this is implemented via an extra loss term. So for example, in a setting where I'm doing classification, my total loss will be some, does this have a laser? No, will be some cross entropy term, LCE, plus some DA term, LDA. And in this sense, this loss is semi-supervised because I have a supervised term that I'm using with the labels I have, but I'm doing some unsupervised learning, which is promoting this sort of robust feature learning. And then sort of diagrammatically, this is meant to illustrate what training with domain adaptation may do. So in this case, you can see I've trained a classifier that can learn maybe some division between my classes in my source domain, but when I go to my target domain, it's quite messy. The idea behind domain adaptation is to learn some division that performs across both the source and target. And so this is not a prescription for universal generalization. I would argue that maybe foundation models are starting to be a prescription for universal generalization in the naive setting that nothing is out of distribution if you make everything in distribution. But this is something that, if you're in a specific setting, if you want a model to generalize, this can be beneficial. Actually, I should pause if there's questions. Cool. So, like I said, domain adaptation is not a new idea. And so in this sense, I've defined the domain adaptation zoo This is borrowing the architectural zoom from Michael Bronstein, who's a big name in geometric deep learning. So we have all these animals in the zoo, and basically all these animals have something wrong with them. I will be focusing on what's wrong with, I guess it's the bull, right? I'll be focusing on what's wrong with the bull and what's wrong with the cheetah down here. But yeah, these all have something wrong with them. And in particular, MMD, which was the bull, maximum mean discrepancy, is this training technique that uses a kernel norm to sort of learn features that persist across data domains. But by virtue of you using a kernel norm, you define a kernel, you have to tune your hyperparameters for your kernel. It's very specific. I can train a model on MMD for one data set, but it will not work on another data set a priori. Optimal transport is something people have been using a lot these days outside of domain adaptation, but optimal transport can be expensive. So the idea behind our algorithm is to introduce a new model to the zoo, which we call SIDDA, standing for Sinkhorn Dynamic Domain Adaptation. And for no particular reason, I have made SIDDA a T-Rex. But SIDDA will have the properties that I'll convince you is that it's data set agnostic. It'll work on across data sets with no hyperparameter tuning. Automatic, again, no hyperparameter tuning. And it's cheap. It'll scale similarly to cheaper domain adaptation methods, despite having the expressivity of full-blown optimal transport. So, okay. So the Sinkhorn divergence is something that's going to be important, like the name suggests. So this Sinkhorn divergence is a class of optimal transport distances. So the optimal transport problem is a very classic problem. This is a problem in which you're interested in computing the minimum cost of transporting probability mass from some distribution mu to some distribution nu. And compared to other statistical notions of distance, like the KL divergence, the optimal transport distance inherits some really nice properties about knowing more about sort of the manifold that the data lives on, rather than just density overlap. So it is more expressive than something like a KL divergence. And in recent years, optimal transport has been something that people use more often because of what's called entropic regularization. So this regularization has made the OT problem convex and differentiable such that I can solve it numerically. But it has introduced a bias at this cost. So what does this bias look like? So this is what the regularized optimal transport looks like mathematically. So here I have OT sigma of mu nu, where mu and nu are basically empirical distributions of my latents. And sigma is controlling the strength of the regularization. So what I'm interested in here, right, is I'm computing the minimum of this quantity in the brackets. And is this the legend? Oh, it just doesn't show on the screen. I'm computing the minimum of this quantity in the brackets, right? And this first term is saying, let me minimize the transport costs, the transport plan being gamma ij. And the second term is this entropic regularization, where H is the entropy and sigma controls the strength of this regularization. And then any transport plan gamma I find has to satisfy these two constraints here on the right. All these equations here on the right are saying is that any probability mass that is leaving mu is going to nu and vice versa. And so in practice, much of the expense in computing optimal transport costs actually comes from finding gammas that satisfy these relations. And so what's a little difficult to see here actually is that if I were to compute OT sigma of mu comma mu, right, the cost of transporting probability mass nowhere, this would actually be non-zero. So this regularization has introduced this bias, and the Sinkhorn divergence is meant to correct this bias. So the Sinkhorn divergence is defined as a linear combination of these regularized optimal transport terms. And this linear combination that they've defined corrects for this bias. And the Sinkhorn divergence also admits this very, very nice property that we're going to be interested in that if I take this regularization sigma and interpolate it towards infinity, the Sinkhorn divergence actually becomes dual to a kernel norm. And in fact, it becomes equivalent to maximum mean discrepancy for bull in the zoo. And then similarly, if I take the regularization to zero, it becomes unbiased optimal transport, the cheetah in the zoo. So basically what we're going to want to do, what we're going to be interested in doing is specifying our sigma parameter in a way that we can enjoy the benefits of both. That we can be cheap, but we can also be expressive. And this is going to be sort of the crux of our algorithm. I'll pause here for questions as well. Yes.
Sorry, can you explain more about the sigma and H there, you've got the drop regularization. So you said that introduces bias.
Yes,
Can you say why that is?
I see why that is. I mean,
Or just tell me about the purpose of making, why you add that regularization in? Does it just make the optimization better?
yes, I mean, basically what this is smoothing out the plan. So without this entropic regularization, there is no guarantee that, you know, OT without the sigma is differentiable, or it could be quite like spiky, you know. I don't know necessarily the specifics. There's also like a hidden algorithm behind this, and that there's a algorithm called Sinkhorn's algorithm that actually iteratively computes these gamma IJs. But my understanding is that without this regularization, this just becomes incredibly expensive. So at the cost of force training some of the information, which is what this entropy is doing, just smoothing things out, you can compute this in a more manageable way. I hope that answers it. Yes?
So at a very basic level, could you explain to us how the concept of they use for solving the problem of the main adaptation?
Yes.
You know, my basic understanding of the is it's a metric of how different two distributions are.
Yes.
So it's what you're trying to do to measure the distribution of the label versus unlabeled data. That was not different.
Oh, this is a good question. And I can remind you here. So in this type of domain adaptation, right, what we want to do is align our latents. And what that amounts to at a numerical level is computing some notion of distance between our two latents, Z and Z star as I define here. And for that metric, we're going to use the Sinkhorn divergence. So you need to define a distance metric, and in particular, it has to be a statistical distance metric. And so that's why we define the Sinkhorn divergence for this purpose. So mu and nu here, in this case, mu and nu are going to be empirical distributions over my latent vectors in my source and target domain. Yeah, thank you. Okay, and you know, so I mentioned the sigma parameter is going to be really important for us. So this is a plot taken from this 2018 paper that discussed the Sinkhorn divergence at length. And here they have this generic problem of moving probability mass from this orange circle to this blue teardrop. And here they compare 4 different notions of distance. They have MMD, so this is the Sinkhorn divergence in the limit of sigma interpolating towards infinity. They have the Sinkhorn divergence for 2 different values of sigma. And then they have bias, the optimal transport. So you can see MMD, if we look at all the way at the right panel, does a pretty good job. Gets most of the probability mass over, but you have these stragglers. Both of the Sinkhorn divergences do okay. And then you see for bias optimal transport, we have this pathological effect where the probability mass is sort of compressed onto the support of the teardrop. And so this is sort of at an implementation level, what this bias and optimal transport can do. It can result in this sort of pathological behavior that we're not interested in. Yes.
Is this a projection of a high-dimensional space from 2D?
No, I think this is just a very simple, 2D example, yeah.
And what exactly is the T, so what way does it look like?
I think this is, well, so you have to keep in mind, this is an optimization. So optimization time, I think is the x-axis.
Like kind of the longer around the implementation.
Yeah. These are good questions. Cool. Okay, now with all that background, I think we're ready to actually say what we did. And so as a reminder, I told you we're interested in universally training a neural network with domain adaptation, right? And so what that amounts to, if we're using the Sinkhorn divergence in our algorithm, is finding optimal value or values for this regularization sigma. And as a reminder, our loss has 2 terms in it. So it requires some optimal balancing of our 2 loss terms, our primary learning objective and the loss term that's doing our domain alignment. And so what this amounts to is 2 ideas. The first idea is to dynamically scale the entropic regularization, the sigma in my Sinkhorn divergence, based on the neural network latent space geometry. And so what I mean by that is I can schedule my sigma like so. And what this equation is saying is if the pairwise norm between my source and target domain latent vectors is very large, let me have my sigma accordingly be larger. And that way my Sinkhorn divergence interpolates closer to MMD. It's cheaper to compute but not super expressive, but that's fine. Because we imagine this is a setting that we encounter typically at the beginning of training. Conversely, when the difference between my source and target domain latent vectors is very small, let me have my Sinkhorn divergence interpolate closer to the Wasserstein distance, to unbiased optical transport. And that way it's more expensive to compute, but it's really focusing on these details, the final details for domain alignment. And this is behavior that we would expect at the end of training, right? And in this way, this is sort of similar to a learning rate scheduler, right? But this scheduler is in fact actually controlling the resolution for our domain alignment during training. Okay, the second idea is to treat the loss coefficients themselves as trainable parameters. And so this is an idea taken from this older paper in 2017. But here, so I have my primary learning objective, which in this case is cross-entropy loss, and then my Sinkhorn divergence, which is my domain alignment term. And what I've introduced are these two eta coefficients that are themselves trainable and optimized jointly with my model parameters. And if you're wondering what this log is doing, or if you're wondering why the coefficients are structured this way, this log is meant to avoid the pathology of just me setting, or these etas blowing up to 0 so that these terms become integers, right? So this is a regularization. But in this way, the loss weighting themselves is dynamically adjusted throughout all of training. In practice, what this is doing is basically keeping things order 1. There are sort of more, in the context in which this was introduced in 2017, these terms would actually be likelihood functions, and these etas would have been the 1 sigma uncertainties if they were Gaussian likelihoods. But in this case, what this is doing is basically just making sure not one term dominates over the other, but they're both roughly order 1 during training. And I know this is a very uncomfortable idea. So. Okay, so with these two ideas, we effectively have no hyperparameter tuning required for effective domain alignment. There is no explicit information about the data set being injected anywhere here. There's no hyperparameters related to kernels or anything like that. The only parameters that you have to deal with are sort of the typical ones you would encounter in a supervised setting, right? Nothing extra at the expense of you doing domain alignment as well. Okay, so if you like thinking graphically, this is sort of a graphic interpretation of what our model is doing. So we start with our source and target domain images. Here I've illustrated my target domain images to just be noisy. I pass those through some encoder that is doing my feature learning, right? So either a CNN or an equivariant neural network. Those go then into my linear layers at the end. My model computes predictions on the source domain, and this is used in my cross-entropy loss, so my supervised term. And then the target domain data enters in through the latent vector, which is used in computing sigma, which is then used in my domain adaptation loss term there. So this is a semi-supervised prescription for domain alignment. Good questions. Yes.
So do you always train this simultaneously, or do you have a pre-train on the source domain?
That's a very good question. So we found that a warm-up period, whether you want to call that pre-training or not, I think it depends on the person, but we found that a warm-up period of just doing cross-entropy loss was helpful. But that was more so related to stability with these etas, which I'll talk about a little bit. But yeah, we did effectively use some pre-training on just the source domain. Yes.
So have you tried the foundation model with frozen embeddings, and then just through the second term of this equation?
We have not. Do you have a foundation model in mind?
I think in astronomy.
Yeah, the Aeon one maybe.
So these are galaxy images, right?
I will use the Sun Galaxy images, yes.
So you could use Aeon or
Yeah.
or
That is not something we tried. We did benchmark it with respect to other domain adaptation methods.
yeah.
For what it's worth, this paper was sort of out already before Aeon was released open source. But that is really interesting. I would be interested to see how Aeon does.
And maybe Zubot as well, right?
Zubot, yeah. Yeah.
Maybe you guys should talk about it.
Yeah.
Yeah, of course. Good questions. Okay. Yeah, so I showed you a visual guide for SIDDA. If you like pseudocode, I'm not going to talk about pseudocode. You can just look at our paper if you like pseudocode, but what I will point out is related to these ETAs. So I said that the loss coefficients themselves are dynamic, right? But you can imagine what we don't want, going back to this, what we don't want is the case where the domain adaptation term is completely overpowering the primary learning objective. Because in that case, what I'm doing is I'm actually aligning the feature learning, but I'm not learning anything meaningful in the first place, right? So what we do is we enforce this sort of manual clipping to make sure that the primary learning objective, in this case classification, is still favored over the domain alignment. And this is just something empirical that we found helpful. But of course, if you're interested in a more detailed description, I invite you to take a look at our paper. Okay, now I will show you that this thing works, right? So like I said, we wanted to show that this was a fairly universal algorithm that can work across data sets. So to that end, we studied it on a few simulated data sets. So using this nice package called DeepBench from friends at Fermilab, we generated synthetic data sets of just very simple shapes, also astronomical objects. And then we also used the MNIST M data set. So this is basically MNIST with fun backgrounds. And then for our target domain, we induced perturbations that are relevant for us as astronomers. So in particular, we studied Poisson noise, PSF blurring, and combinations of the two. And this is the extent of the simulated data sets that we studied. And then, of course, we also wanted to study this on real data. So to this, we used the Galaxy Zoo Evo data set, where here in the source, we have 3-channel images from SDSS for these six morphologies. And then we use the DESI legacy imaging surveys as our target domain. And so these, of course, still had labels anyways, but we just didn't use them. We were only using labels from SDSS, seeing how well we can perform on the DESI images. Okay, so we're going to spend some time talking about this. So you can see these are our data sets that we studied.
Really quick question.
Yes.
You said you don't use the labels for the DESI data.
Yes.
But during training, don't you need the labels to get the Z star, the logic?
No. Yeah, good. So in our method, there's no target domain labels required. The only labels we're using is from our source domain. So the data
just run the encoder and get Z, I guess, for the target. Right.
Yes, so Z and Z star we get actually from the decoder, but yeah, there are no labels. There's no supervised training being done with our target domain where we're generalizing to. Yes.
Sorry, yeah, could you go over so how you use, so I guess you first train on the SDSS data and then the other, like, can you go over that again?
Yes, yeah. So would you prefer?
That's when each data set comes in.
Yes, so I mean, the images for both data sets are coming in at the beginning. So I'm passing in, and these don't necessarily have to be one-to-one, but per batch, I'm passing in a bunch of, for training at least, I'm passing in data from both the source and target domain. So SDSS, DESI. And they're both going through my encoder, right? My CNN or my equivariant neural network. Here is when the discrepancy in how the source and target domain is treated comes in, because my source domain has labels, right? My SDSS images have labels.
Yeah.
So I'm doing supervised learning with SDSS. SDSS labels are entering in my cross entropy term. But my DESI images don't have labels. So the model is learning features from DESI through my Z and Z star, where they're used in computing my sigma, which is then used in my domain adaptation loss. So I'm doing unsupervised learning as far as how DESI is entering the picture. The only supervised learning I'm doing is with SDSS. Yes.
So then Z star, that sees and they're being compared across the whole batch?
Yes.
Pairwise?
Yes. Yes, yeah. Does that make sense?
Yes.
Okay. But yeah, so for all the results I'm talking about, our target domain does not have labels. Of course, for benchmarking purposes on the test set, I have labels just to show accuracy, but as far as training goes, the only labels are coming from my source domain. Yes.
I'm wondering how changing the class frequencies between the target and source domain
It's a good question.
affects the.
Yeah, that's a really good question. So in that So that of course is very relevant. That would no longer be a covariate shift. Yeah, it would be a different type of domain shift. And yeah, we did not study that. My hunch is, especially at a per batch basis, you know, if your batch is sufficiently large, that your empirical distribution per batch at least includes some of each label. My hunch is that it would be okay. But in the setting that, like, let's say there's several order of magnitude discrepancy between certain classes, I think the model would definitely struggle on the class that is not represented as well. That's a good question.
So, wait, so it's assuming that those factors are proposed in income, right? Or not?
So the model isn't, but the type of setting we're operating in, this so-called covariate shift, is operating under that assumption, yes. Yeah, the only sort of free parameter, the only thing that's changing is the data distribution, the quality of the data distribution. But what you're asking about is the conditional distribution of the labels. And the conditional distribution of the labels is roughly the same in this setting. Good question. Cool. Okay, yes, we did this. Oh, right, results, okay. So yeah, we have our data sets here. And we studied effectively 4 sets of models. So we have a regular CNN. The -DA denotes that I trained it with SIDDA, whereas without that, it's just typical cross entropy loss. And I have a D4 equivariant model, also trained with SIDDA, which I call D4DA. And so there's a few things you want to see here. First, I invite you to see how the target domain accuracy between the CNN and the D4 differs. So, you know, stepping more big picture, not just sort of me selling you this algorithm, and we're talking about how do we actually make models generalized. This is an instance in which just including symmetries is actually increasing performance quite a bit. Now, if we want to pay attention to Galaxy Zoo Evo, that's a 10% difference in target domain accuracy and a 5% difference in source domain accuracy just by training with an equivariant model instead of the CNN.
Sorry, D4 is the equivariant model.
Yes, so this is the dihedral group of order 4. So basically the symmetries of the square, discrete rotations and flips.
So can you, is that just happening in the augmentation or are you changing the architecture?
This is the architecture. So this is an so data augmentation, in a sense, induces equivariance. This is explicit equivariance. So this model, for example, if you like thinking about code, my CNN was written in PyTorch, but my D4 equivariant model was written in ESCNN, which is a package explicitly designed for writing equivariant neural networks. So the feature learning in my D4 model is strictly adhering to equivariance, whereas I don't get that strict of a symmetry just by data augmentation. Yes.
So for regular CNNs, when you rate the target accuracy, doesn't mean you still can train only on the source data and then just apply without any.
Yes, exactly. So for CNN and D4, source is what it was trained on. Of course, this is test set, right? Source is what it was trained on, and I just tested it on the target domain did not enter the training at all.
Another question. So I noticed that for CNN, when you apply domain adaptation, for most of the scenarios, the source accuracy stays about the same, but
Yes.
for AstroAI specifically, it's worse by a factor of 10 or so. I mean, like
For this one, right?
yeah.
Yes. So this is, yeah, that's a good point. This is something people do see in domain adaptation.
Mhm.
And if you sort of want an ideological way of thinking about it, I think you should come to terms with the fact that I think most models do overfit, and sometimes it's actually useful. So this is a setting in which the CNN was probably actually overfit, slightly at least.
So what do you mean overfit? So you tested on deep things.
So yeah, because
Test data.
Yeah, because what this is showing is that with domain adaptation, it learned features that persisted across data domains and performance went down. So what that's saying is some of the generalizable features actually, like didn't. This is of course, yeah, we only see it for these 2 examples, but this is something that people do sometimes see in domain adaptation, yes. It is interesting to note though that we didn't observe this for the equivariant model.
You mean for D4?
Yeah, so for D4, at least not like drastically, something about this data set maybe. Yeah, sorry, I see it.
Sorry, do you have something similar to this, but with like some other method, like any, like prior score or
So I do discuss calibration as well. Yeah, but after this is just accuracies for now, because there's other things to get out of this plot. So yeah, the first thing, of course, was that our D4 model performs better than CNN. So this is just simple training, right? The second thing is that the efficacy of SIDDA is actually more so with the equivariant model than the CNN. And I have like the very last slide discusses an idea for why this is. But for example, if we look at this simple shapes data set, you know, we get like a roughly 30% improvement with the CNN, but that becomes almost perfect domain alignment in the case of the equivariant models. These equivariant models are sort of predisposed to perform better when trained with SIDDA. And then lastly, you know, stepping back a bit, because this isn't just to talk about this training algorithm, it's about training and architecture. I just want to point out to you, in the case of Galaxy Zoo Evo, if we compare just the CNNs, the most naive thing one would do, with everything we prescribe in our paper, that's a roughly 13% increase in the target domain. So these are sort of tangible improvements you can get by making informed decisions in both your architecture and your training. Get this back. These are all great questions. Thanks. Before I move on. Yes.
Do you expect even more improvement if you change to a smooth group, like SO2 or something?
Yeah, so I will share this. So equivariance is like a double-edged sword. And I'll show a plot that illustrates this. There is this, I guess lore isn't the right word, but you know, there's a sweet spot for how equivariant one should be. Because you can imagine, especially in the case where you're dealing with noisy images, as you approach, in this case, O2, the likelihood of symmetry being broken by the noise is higher. And so Robin Walters, my collaborator a few years ago, released this paper called Approximately Equivariant Models, where you can be equivariant to some epsilon tolerance. That is, I think, like a sort of more manageable long-term path of like getting like full equivariance. I think O2 in this case actually would not do that well. And I do have a plot that shows something along those lines. Yeah. Question. Cool. Nice. Okay, yeah. We already discussed this. Cool. Next thing. So if we go back to how we scheduled this sigma parameter, right? The regularization for my Sinkhorn divergence. I said what would be great is we wanted to exploit the pros of both limiting cases of the Sinkhorn divergence, right? It would be great if we can be as expressive as the Wasserstein distance, but also as cheap to compute as the kernel MMD. And so this is on one of our data sets, this is MNIST-M, but here I'm benchmarking SIDDA for both of our models compared to both the Wasserstein distance and MMD. And what this is showing is, in this case, SIDDA is performing comparatively, in this case, a little better, but I don't think you should take any value from that, just comparatively to the Wasserstein distance. It's the best case scenario. But when we look at its compute wall clock time, it's actually comparable to MMD. So in this sense, by scheduling our sigma parameter in this way, we did get the best of both worlds. We have a distance metric that scales as cheaply as MMD, but performs as well as the Wasserstein distance, which is exactly why we did that sigma scheduling, like I said. Okay, so I wanted to ask a question about calibration. I'm going to spend a little bit of time on calibration because you'll see, it's just looking at a lot of numbers. But yeah, the idea behind a calibrated model is, like, especially when we're doing classification, in the real world, people don't just care about this class was chosen. People care about probabilities. And in the context of classification, people hardly interpret the things that a model is outputting as probabilities or well-calibrated probabilities. And so calibration is extensively, like, I think, getting more popular in the ML world because people want to make sure that, you know, if you're treating your neural network effectively as a surrogate for a likelihood, is it actually representative of true population, right? And so most models that we encounter and we train are actually not calibrated. But what we found with SIDDA, and you know, it's not worth looking at all these numbers, but maybe if you just want to look at the bold, So what we found that with SIDDA is if we looked at two sort of very useful metrics for calibration, that is the Brier score and the expected calibration error, SIDDA improved calibration with both the CNN and the D4 model, and the equivariant model, the D4 model, was better calibrated than this. And so domain adaptation methods are not like sort of canonically considered to help calibration. But this is something we observed with SIDDA. Well, okay. Yes.
Number, but do you observe that it improved or like it improved both in your source and your target when you look at like the prior support the factory? Or do you see still like a little bit of decline on the side?
So if I look at the bold, yes, source and target improves.
They both improve.
Yeah. Sorry, it's been a while since I've looked at this table, but yeah, just by looking at the bold.
But I mean, that would fully justify what you said before about overfitting. Like if it here,
Yes.
it improves both in Brian, they can.
Yeah. Yeah, so I guess depending on who you talk to, they might care more about a well-calibrated model versus an accurate model, you know. Right. Yeah.
Maybe in the talk to approach to data sets, I seem to still the CNN performance
Yeah.
better on the source, right?
Yeah, it's, and I really, I don't know. You can see it wasn't, at this point, it's like a third decimal place difference. There's something, I don't know why that was the case. It seemed, at least for the astronomical objects, there's a sort of weird behavior as well with the accuracy. So maybe it's something with the data set. For me personally, what I care about most when it comes to these results is the real data set, the Z Gauss Zoom Evo. But yeah, that is something that we observed as well. And I don't have a good explanation for why that is. Cool. Now just some analysis stuff. I guess, how am I doing on time? I'm okay. So frequently, and I'm sure you guys have seen plots like this. Everyone likes showing plots like this. But this is actually something people frequently do in the domain adaptation literature, right? Because our latent vector space, et cetera, is a very foundational object, and it's natural to see what is actually happening in that space. So this was an isomap projection of our latent vectors for all four of our models, so the CNN with and without SIDDA, and also for the D4 model. And when looking at these plots, there's two things you want to see. You want to see better clustering. So in this case, this is a latent space for M-NIST M, so there's 9 digits, 9 clusters. You want to see better clustering, because that corresponds to better feature extraction. And then here, I'm also plotting both the source and target domain on top of each other, so the Z and Z star. And I know this is a little hard to see, but you want to see better overlap between the source and target domain, because that corresponds to better domain alignment. And so we computed some observables on this, notably what's called the silhouette score. But I think what's more sort of, I'll step back here to see it with you guys. What's more shocking is like the visual contrast between the CNN, where you see I have no sort of well-defined clusters. It just looks like a big blob. And then we compare that with the equivariant model with domain adaptation, where you see I do have well-defined clusters. I have good domain alignment. At a latent space level, you can see that this is working. And so again, this is a reminder that this isn't just about how I'm training the model. It's how it's an architectural choice in addition to training, which is how we see this direct evidence in the latent spaces. Cool. So I said that our method amounted to basically automating these 3 parameters, right? We have this sigma, this regularization for the Sinkhorn divergence, and our 2 etas for trainable. And so naturally, it's interesting to study what these parameters are doing during training. So in this case, what I have is I have the regularization for the Sinkhorn divergence sigma plotted in yellow. And then I have the inverse squared of my etas, which is basically just the coefficients of my losses in red and blue. And the more transparent curves, if you recall, the more transparent curves are the evolution of these parameters without this clipping I did. And so there's a few things we can take away from this plot. And the first thing that we see is that the clipping of these coefficients stabilizes these etas throughout training, especially at lower epochs. This is a log scale on the x-axis. So we see this clipping was sort of like well motivated because we see it's more stable, but also we see that even without the clipping, they converge to similar values by the end. So maybe this wasn't like completely necessary, but at least was nice from the point of view of stability during training. And the second thing we see that the Sinkhorn plant interpolates closer to MMD at the beginning of training because it's more order one. And then by the end of training, it's interpolating closer to pure optimal transform. So if you recall, this is exactly what we had sort of intended with how we scheduled this sigma value. Because at the beginning of training, my source and target domain latents are very different. So my Sinkhorn divergence is going to interpolate closer to MMD. It'll be cheaper to compute. But by the end of training, presumably by which the domain alignment has started working, I'm interpolating closer to the Wasserstein distance. And this is exactly what we see here. Okay, and then, of course, the last interesting thing is to wonder, why do we see this like sort of inherent benefit of using equivariant models over CNNs, right? And to that, I don't have a perfect answer, but I have a hunch, which we discussed in our paper. And so there's this nice result from 2022 in the domain adaptation literature, where they say that there exists a lower bound on the target domain error, and it's a function of the Jensen-Shannon distance between my source and target domain distributions. And so I don't have the functional form of the JS distance written, but it's basically a linear combination of KL divergence terms. And so what this is saying is that the JS distance between the source and target latent vectors is the fundamental objective. And a lower JS distance means they're more similar. And so what we're looking at here is, again, this is for MNIST-M. What we're looking at is the evolution of the Jensen-Shannon distance for a bunch of models. So I have my CNN and my D4 model, which is what most of my results discussed. But I also study equivariant models of varying orders going up to D8. And there's a few things we see here. First, if we look at this little q here, so this is just cross entropy training. And here we see that the D8, the D8 model manifestly has the lowest JS distance. And it's a little hard to see, but this sort of, this trend continues as we go in decreasing orders of equivariance. So the CNN has the largest JS distance and the D8 model has the lowest. So this is at least one aspect of analytic evidence for why these equivariant models are generalizing better. That their source and target latent distributions are inherently smaller due to this constrained feature length. And then in the main panel of the plot, what we're doing is we're tracking the JS distance as we train the models with SIDDA. And you can see, with the exception of D8, the JS distance monotonically decreases with increasing equivariance. And so someone had asked earlier about what the right degree of equivariance is. And here we see the D8 model actually starts to overfit. And so what we think is happening here is this is an instance where the equivariance constraint is too strict. And you're losing out on some model expressivity due to the super constrained feature learning. And so, yeah, the better performance with and without SIDDA can be attributed to the smaller JS distance. This is some evidence what people sort of qualitatively believe, that is, symmetric features are generalizable features. So, okay, and then to conclude, I focused just on classification today, but I hope I've emphasized too that like the framework we put together is very modular, very data set agnostic. So you could easily just replace LCE with LMSE or negative log likelihood, whatever, right? And this is in fact stuff I'm working on right now, and we see that it does work. So SIDDA can be easily extended to other loss functions, and it can help you generalize between simulated and real data, clean and noisy data, lab-based field level, varying resolutions, etc. And it can achieve effective domain alignment in all these cases with no hyperparameter tuning and no labeled data in the target domain. And so we hope this is something that's useful for people that need to generalize in their work. So this is the recap. I will leave this up, and yeah, thank you for all the questions.
Thanks very much for a really exciting talk. Let me just switch out. We've got about 10 minutes for questions. Anyone want to start off? So I'm really interested in how this works for astronomy, where we've got a lot of simulations applied to real data, and then also transferring from one survey to another where the resolutions are different.
Right, yeah.
Could you talk more about how that would work with changing the resolutions? Like, would you still expect to see the domain shift working?
Yeah, I think, so it's funny, so like, I was at a talk a while ago from Francois Lenoux talking about their new foundation model, and I'd asked if Rubin DP1, if it would work on Rubin DP1. And he had said no, because Rubin DP1 is still out of distribution, so out of distribution from the training set. So I think resolution is one of these things that really has the potential to like trip up generalization efforts, even at a domain adaptation level. For what it's worth, when we were considering SDSS and DESI, like those images were processed in a way that they sort of had similar resolution. I think, yeah, I don't have a good answer for this because it's not something I studied, but my hunch is that actually that resolution is on the harder end of the spectrum, adjusting to generalization. And I'm sort of supported by this evidence I've seen from this very impressive foundation model that came out of CCA, where they also said they struggled with resolution, so. Yes, sir.
So, following up on this distribution question, so is there a native built-in way to distinguish whether your source and target are compatible in this sense, or basically there is some, I know, some clear metric? If you don't know the target labels, you can directly check the classification accuracy. But these are some metrics that you can use, like this is out of distribution.
Yeah, that's a good question. Yeah, so like how can I quantify if the model's performance?
Just gotta
Yeah.
tell during training or after training, but okay, I don't expect it to work well.
So yeah, what you can do, right, is you can look at, like, let's say I deploy my model on labeled data test set, and then I also do that for an unlabeled target domain, and I just look at the distribution that comes out, right? And so this also comes back to calibration, right? Because you can imagine if I don't have labels for my target domain, and my model is just predicting only one class, then like even without labels, I know this model is probably garbage. But if the distribution across labels at least semi-matches what I have in my labeled setting, again, this all comes down to like being very precise about what shift, what type of out of distribution shift you're dealing with. Because again, if you don't expect that the conditional distribution of labels is the same for the distribution or the data set you're generalizing to, then you can't use this as a test. Yeah, I don't know if I have a great answer for that, except just looking at the distribution of what the model is predicting. This is not something I touched on, but in version 2 of the paper, the reviewers had asked us to test this model in a different imaging modality setting. So generalizing between SAR, so there's some version of infrared images and visual. And in that setting, we actually found that it did not work very well. So there are limits. And in particular, we've seen that really different imaging modalities.
How exactly do you see it? Do you see it by comparing with the ground labels, or you saw it?
Yeah.
Out of training?
I mean, since I'm sharing my screen, I might as well show up a plot. Because we can see so this is the same latent space plot I showed, but this is for this data set where the imaging modalities were different. And so yeah, this just looks like garbage, right? So even if you didn't have test set labels, you can use this as a diagnostic for whether my model is performing well or not.
And why is it domain even for source?
Because it wasn't learning the source that well either. So yeah, that's like an order 1 test, is if you can't learn your source, forget about generalizing to your target, but yeah. Yes?
They kind of along those lines, in checks, images versus spectrum.
No, we have not thought about time series. If I was doing this with time series, I could very well just replace my encoder with, self-attention or an RNN or something that actually learns time series. But we only tested this on images so far. Yes.
Because when we were dealing with text, we also have the domain application question. I don't know.
So I'm not too familiar with text. What is out of distribution when I'm working with text? Like a different language or?
So different language terminology that.
I see.
For example,
where the label can be the same, but it's the feature of the language are different.
I see. I don't know if I have a great answer. What comes to mind is, I guess that's the point of self-attention though, right? Is to learn contextual information. So maybe you might not need domain adaptation in that case. I'm not sure. I haven't really worked much with text.
So one of the main use cases of domain adaptation is when you've got limited sort of target data, right? How much, right, there's not enough there, right? So how much
No
data?
label.
No label, so how much data do you need?
Yeah, that's a good question. This was one degree I wanted to study, in this paper. And I did it, but, in this case, so the target domain data in this case was always sort of roughly the same order of magnitude as the train. And, I think it's interesting to wonder like how much or what's the least amount of target domain data I can have. But I think the setting in which people are operating more often is actually that you have way more unlabeled data than labeled data. And so were you asking about the amount of labeled or unlabeled data?
Yeah, actually, probably not labeled data. Sometimes we do have a little bit of labeled data in the.
I think the cutoff is so in this case, like the source domain learning was horrible as well. So if you have enough labeled data that your model can, according to your internal gauge of good enough, if your model can learn the source data well enough, you have enough data for that, then I think that's enough. And so whether, and that of course is a use case example, right? Like whether that's order 1,000, order 10,000, order 1 billion. I think the least amount of data for your model to learn the source enough alone, so just like cross entropy, MSE, whatnot, is what you need. And then from that, like the sky's the limit with the amount of unlabeled data you have.
Right. But how do you change your architecture if you do have target labeled data? Or do you change your author?
So if you do have target labeled data, just throw that in with your source, right? Like, you're still doing unsupervised learning with the data that is not labeled, whether it's coming from your source or target. Yes.
In the beginning, you had many generalization techniques, and you're touching, I guess, one of them
Yes.
by doing this. Can you comment on your method versus other sort of?
Yeah. This is in regards to the zoo, right?
Yeah.
So I can comment on one of them, and it is the hyena domain. Forgot what this means. It's adversarial, domain adversarial neural networks. So this is sort of the setting where you're doing adversarial training. So basically, you have two decoder blocks. One block is doing the learning, and the other block is trying to, like, in an adversarial sense, see if it can distinguish between source and target. And so this is a fundamentally different type of domain adaptation than MMB and OT and these as well. Because architecturally, this is quite distinct as well. And what is sort of empirically true at this point is that these models have the potential to perform better than these distance-based methods, which is what I talked about today. But these come at the expense of being really, really hard to train. So it really depends on your use case. I've encountered people that said that they've tried to train DANs and like they either worked or it failed horribly. It's really hard to tell. Whereas with these distance-based methods, these distance-based methods, you can at least go into them semi-confident that it'll work, and it won't be too much extra work from your point, especially with something like SIDDA. But if, like, for example, you applied SIDDA and it wasn't everything you wanted it to be, I would tell someone to try a DAN, but just get ready to really like fight with it to get it to work. So yeah, everything has the pros and cons.
So I think that might be time. Thanks everyone for joining. So Sneh will be here for the rest of the day, I think.
Yes.
And then he's also just down the road in Northeastern in Boston. So please feel free to send him an email. And thanks again.